next subtopic is second order homogeneous differential equation with constant coefficients. Second order homogeneous differential equation with constant coefficients is of the form a subscript 2 d square y all over the x squared plus a subscript 1 dy dx plus a subscript o y is equal to 0. Now, this is the one we call second order homogeneous differential equation with constant coefficients, where a2, a subscript 1, a subscript 0 are constants. Now let's look at method of solution. First of all, let's consider this first order. Let's consider this first order homogeneous differential equation. Consider this. Dividing through by a subscript 1, that is the coefficients of dy dx, we will have dy dx plus a subscript o y all over a1 is equal to 0, which means that dy dx will be equal minus a subscript o all over a subscript 1. Now, if I put m is equal minus a subscript o all over a subscript 1, then what I will have will be that dy dx will be equal my. Look at that. My. And then by separation of variable, we know that we can write this as dy all over y is equal m dx. So integrating both sides, we will have integral dy all over y is equal integral m dx. Now this side will give us ln y will be equal m x. You know, if you integrate this with respect to x, we have this. Now taking log of both sides, we will have that y is equal exponential mx. This becomes the solution to the first order differential equation. First order homogeneous differential equation with constant coefficients. Now observe that the constant of integration is neglected here. Now from here, let's relate it to second order differential equation. If y is equal to this, so let's go to second order. We know that second order is of this form. We have a subscript 2 plus a subscript 1 dy dx plus a subscript 0 y equals 0. That is second order homogeneous differential equation with constant coefficients. Now, if we now see that y is equal exponential mx. It means that y prime will be equal m exponential mx. Y prime prime will be equal m squared exponential mx. So we are going to put these values in this equation. Of course, we know that y prime is the same as dy dx. Y prime prime is the same as d square y all over the x squared. So putting it in this equation, we will have that a subscript 2 m squared exponential mx plus a subscript 1, then we go here to y prime, m exponential mx plus a subscript 0 y is exponential mx is equal 0. And then we also see that we can write this as a subscript 2 m squared plus a subscript 1 m plus a subscript 0 exponential mx is equal 0. Now look at that. I just factor out exponential mx. Now a subscript 2 m squared plus a subscript 1 m plus a subscript 0 is equal 0. Exponential mx is not equal to 0. Now, this particular one, that is a subscript 2 m squared plus a subscript 1 m plus a subscript 0 is equal 0, is called auxiliary equation. Auxiliary equation. This is what we call auxiliary equation, which could be solved in the normal quadratic pattern. You know, this is quadratic in n. Now the solution to this is given by n is equal minus a1 plus or minus square root of a1 squared minus 4 times a2 times a0 all over 2a2, a subscript 2. That is 2a. You know, this is quadratic formula. So we can use the quadratic formula to solve this auxiliary equation. Alright. Then, to solve this auxiliary equation, there are many cases that we want to consider. Case 1, when the roots, of course we expect m1, m2, we expect two roots in the auxiliary equation. So case 1, when the roots are distinct, when we have distinct roots. When we have distinct roots, the two linearly independent solutions are exponential m1 and exponential m1 and that is exponential m1x and exponential m2x. The general solution or the complementary function. General solution or complementary function is yc is equal c1 exponential m1x plus c2 exponential m2x. That will be the complementary function. Now we also have another case. Case 2. When the roots are coincidence. Coincidence. You know, when we have coincidence, we talk about equal roots. That is M1 is equal M2. In that case, the two linearly dependent solutions are exponential M1x and exponential M2x. Don't forget that M1 and M2 are equal in this case. Alright. The complementary function is yc is equal. Now, note the complementary function. C1 exponential M1x plus C2x. Look at that. C2x exponential M2x. That will be the complementary function. In the case where the auxiliary equation has equal roots. Now let's look at case 3. Case 3. When the roots are imaginary, that is, I'm talking about complex roots, where we have a plus or minus bi. You know that complex number is of that form. So complex roots will be in that form. So if we have such roots, the two linearly independent solutions are exponential ax cos bx and exponential ax sin bx. Then we now see that the complementary function okay, that is the general solution, you know, but we'll be calling it complementary function when we look at a non-homogeneous. So the general solution will be given as is yc is equal C1 exponential ax plus C1 exponential ax cos bx plus C2 exponential ax sin bx. So we have about 3 cases now. We have case 1 when the roots are distinct. The general solution is C1 exponential M1x plus C2 exponential M2x. Case 2 when the roots are coincident. We have that the general solution, let me call it general solution. The general solution is yc is equal C1 exponential M1x plus C2 exponential C2x, you know, see this, C1, then we have C2, then we have x. Very important to note. Exponential m2x. Same thing happens for this imaginary root. See the general solution, which is given by C1 exponential ax cos bx plus C2 exponential ax sin bx. Can also call this the general solution. So the general solution is this. So let us take these three examples so that we can demonstrate the three cases that we have just said. Now, solution of 1. We have y prime prime minus 6y prime minus 16y is equal to 0. Now, let y is equal exponential mx. We know that y prime will be m exponential mx, and then y prime prime will be m squared exponential mx. Now, putting this in this equation, we shall have that m squared exponential mx minus 6m exponential mx minus 16 exponential mx is equal to 0. So that m squared minus 6m minus 16 exponential mx will be equal to 0. M squared minus 6m minus 16 is equal to 0. Exponential mx is not equal to 0. So we are going to solve this. This is quadratic. Now we know that in this quadratic that m squared minus 8m plus 2m minus 16 is equal to 0. That is, I want to use factorization to solve. So we have that m squared minus 8m plus 2m minus 16 is equal to 0. So we have m minus 8 plus 2 m minus 8 is equal to 0. Now what happened here? You know, we'll collect this as usual. So m plus 2 is equal to 0, or m minus 8 is equal to 0. We now have that m is equal minus 2, or m is equal 8. So the two linearly independent solutions become exponential minus 2x and exponential 8x. That is what we are saying. We'll have it this way. And then the general solution becomes yc is equal c1 exponential minus 2x plus c2 exponential 8x. It's just that. So when you substitute this and then you just solve for the values of m, of course you have m1 and m2. So you substitute in the general solution, and that's all. It's very simple. Now we'll do 2. For 2, we see that we have y prime prime minus 10 y prime plus 25 y is equal to 0. Now, let y is equal exponential mx, so that y prime will be, as differentiating this y, have m exponential mx, and then y prime prime will be m squared exponential mx. Now we are going to put in this equation. We start with y prime prime, which is m squared exponential mx minus 10 y prime, which is m exponential mx, plus 25y, which is exponential mx, is equal 0, which will be written as m squared minus 10m plus 25 exponential mx is equal 0. So m squared minus 10m plus 25 is equal 0. But exponential mx is not equal 0. Now in this case, we see that 5 minus 5 can give us 10. And so minus 5 times minus 5 can give us 25. We know that in quadratic equation, this is quadratic equation when it is in unity. So it's very simple to solve this. So we have that m will be equal 5. This is m1, m2 is what? 5. Now look at this case. In this case, this was distinct roots, minus 2a. And we have the general solution in this way. But the next case that we are taking here is coincident roots, that is equal roots. You can now see here that m1 is equal m2. So in this case, we say that the two linearly dependent solution will be exponential 5x and exponential 5x. And so the general solution becomes yc is equal c1 exponential 5x plus c2x. Look at that. In the case of equal roots, we put x before we now put exponential 5x. This x was not in this one, but this one is different, distinct roots. So that is just the difference. So it's very simple to solve second order homogeneous equation with constant coefficients. Now for number 3 here we have y prime minus 4y plus 13. Yes, plus 13y is equal 0. Let's look at that. Number 3, solution of 3. Y prime minus 4y plus 13y is equal 0. So we know that y will be equal exponential mx. Y prime will be m exponential mx. Y prime will be m squared exponential mx. From what we derived that time. This is the solution that I can use. So if we substitute this in the equation, we will have m squared exponential mx minus 4m exponential mx plus 13 exponential mx is equal 0. Okay. So we also have that m squared minus 4m plus 13 exponential mx equals 0. Meaning that m squared minus 4m plus 13 is equal 0. But exponential mx is not equal 0. Yes, we assume that exponential mx is not equal 0 because you can see that is even what we have for the linearly dependent and independent solution. So it cannot be equal 0. Now here, m squared minus 4m plus 13 is equal 0. Now solving this, let me use a formula method so we can go straight. You see that m will be equal 4, that is minus b. 4 plus or minus 4 squared minus 4 squared minus 4 times 1 times 13 all over 2 times 1. And this will give us 4 plus or minus, this is 16, so 13 times 4, 12, write 1. This times this is 4 plus this, we have 52, minus 52 all over 2. Anyway, but we see that 52, 16, we have 6, 36, alright. So this place we call 4 plus or minus 36 all over 2. Of course, this is complex roots. So we know this, and we know how we can solve this in complex numbers. If you have the knowledge of complex number, you see we can solve this to be square root of 36 times square root of minus 1 all over 2, which is the same as, this is 6. This is 6. So, and this is 4. So we have 4 plus or minus 6r all over 2. In complex number, square root of minus 1, we represent it by r. Now this will give us 2 plus or minus 3r. Look at that. Because this divided by this divide this. Now, the two linearly independent solution will be exponential a, this is a. This is a plus br. This is taking a, this is b. So exponential 2x cos 3x, that is cos bx. We said that from what we just showed. We said that the two linearly independent solution will be exponential ax cos bx plus, and exponential ax sine bx. So this will be exponential 2x cos 3x and exponential 2x sine 3x. Now the general solution, YC, general solution will be C1 exponential 2x cos 3x plus C2 exponential 2x sine 3x. So that is the general solution. It's so simple to solve. So simple. So we'll look at next subtopic, which is non-homogeneous differential equation. That is second order non-homogeneous differential equation with constant coefficients. The next subtopic is second order non-homogeneous differential equation with constant coefficients. The equation of the form a subscript 2 g square y all over the x square plus a subscript 1 divided x plus a subscript 0 y is equal f of x is called second order non-homogeneous differential equation with constant coefficients. The left hand side, that is this side, if equated to 0, gives homogeneous equation. Now this side, Suppose we equate it to 0 without this one. We get back the homogeneous equation that we are solving. So the left hand side, when equated to 0, gives homogeneous equation. Okay. The right hand side is called the particular integral. Particular integral. Which could be solved using any of the underlisted methods. I'm talking about the right hand side. You see, we solve this side as usual. We know how we solve this side. Then this side, which is the particular integral, we can solve it by any of these methods. Number one is what we call undetermined coefficients method. Number two, we have variation of parameters method. Number three, we can solve it by operator D method. Number four, can use the Laplace transform method. Alright, now let's start with undetermined coefficient method and see how we can solve with that. Undetermined coefficients. Method. The undetermined coefficients method depends on the nature of YP. YP is what? Particular, that is the particular integral. Talking about the particular integral, which is the right hand side. So in undetermined coefficients method, the undetermined coefficient method depends on the nature of YP, that is the nature of here. Now, look at it. Case 1. If YP is equal Pn of x, that is polynomial function. Polynomial. We are going to assume, this undetermined coefficient depends on assumption. We assume a function. So, case 1, if Yp is equal to Pn of x, that is if it is a polynomial, we assume function of the form yp is equal a1x raised to n plus a2x raised to n minus 1 plus, we continue till we have plus anx raised to n minus n. We'll assume a function of this form if it is a polynomial. Okay. Case 2. If yp is equal k exponential ax, where k and a are known constants. What happened? We assume yp is equal a1 exponential ax. That is, if yp, that is this side, is exponential function, and in that exponential function we have k, which is constant, exponential ax. So we assume a1 exponential ax, where a1 is a constant. Alright, another one. Case 3. If yp is equal k1 cos bx plus k2 sin bx, or k1 cos bx or k1 sin bx. That is, if it is any of this, k1 cos bx plus k2 sin bx, or only k1 cos bx, or we have only k1 sin bx, where k1 and k2 are constants. Okay, we assume yp will be equal a1 cos bx plus a2 sin bx. Now, let's look at case 4. Case 4. If yp is the sum or product of case 1 to 3. Now, if yp, that is this, the right hand side, this yp here, this side, is the sum or product of this polynomial, exponential, till we use a trigonometric function. If yp is the sum or product of case 1 to 3, then assume the corresponding sum or product of case 1 to 3. So the corresponding sum of products of this assumption that we are talking. See the assumption here. We have assumption here for polynomial, we have here for exponential, we have here for trig function. So if yp is the product of case 1 to 3, we also assume the corresponding products or sum. So that is how it is. Now we are going to take example so that we can use undetermined coefficients to solve it. Look at this example. Given the non-homogeneous differential equation y prime prime plus 6y prime plus 8y is equal to 4 cos 2x plus 5x exponential x. Find the complementary function, B, the particular integral, C, the general solution. And let's pick the solution. The equation is y prime plus 6y prime plus 8y is equal 4 cos 2x plus 5x exponential x. Now, the first thing we'll do is to solve this part by equating it to 0. We'll keep this first and solve this part by the usual pattern. So we have y prime plus 6y prime plus 8y is equal to 0. Alright. Now, we know that for this, that is the usual pattern that we're solving. We know that we'll have something like this. M squared plus 6m plus 8 is equal to 0. That is the auxiliary equation for this, which we know from what we have done. Alright. And then we have exponential mx, of course, is not equal to 0. We should be able to know this from what we have done. Now, if we solve this, we'll have that m1 is equal minus 2 and m2 is equal minus 4. That is because two numbers that when we add we have 6 and when we times we have 8 will be 2 and 4. So if 2 and 4 are the numbers, then it means that the solution will be the roots of this equation is m1 is equal minus 2, m2 is equal minus 4. So that the general solution become the complementary function become yc is equal c1 exponential minus 2x plus c2 exponential minus 4x. We observe that this is c1 plus c2. That is because we have distinct roots. Okay, that is the complementary function. And then we will now talk about this side, particular integral, yp. And we observe that yp is combination of case 1, we have polynomial function here, we have exponential function, we have trigonometric function. So I decided to put the 3 at once so that we can do it one time. And you see that if it was to be only this trigonometry without this one, only this trigonometric function, so we will assume a1 cos 2x. So yp will be equal a1 cos 2x plus a2 sine 2x plus a3x plus a4 exponential x. You see, this assumption is for the trigonometric function. Then why this polynomial is of degree 1, so you have to get 1 and the next is the constant. Alright. Now, yp prime will be minus a1 minus 2 a1, I'm going to differentiate here, sine 2x plus 2a2 cos 2x plus then this a3x plus a4 differentiation of exponential plus then we keep exponential and differentiate here. Of course, when we differentiate here, we will have a3 exponential x. This is products. product rule of differentiating this place. Then yp prime prime will be minus 4a1 cos 2x minus 4a2 sine 2x plus, then differentiation of here. Differentiating here, we will have a3x plus a4, differentiate here, plus a3 exponential x. Then here, when we differentiate here, we still have a3 exponential x. That's that. So this is yp prime, yp prime prime. We are going to substitute in the given equation. Substitute in the given equation. Now, the given equation was y prime prime. So we'll start with y prime prime plus. Start with y prime prime, which is this. So we put minus 4a1 cos 2x minus 4a2 sine 2x plus a3x plus a4 exponential x plus a3. Okay, look at this. a3 exponential x a3. So we can write plus 2a3 exponential x. Alright. Plus 6. Then we enter y prime. And then y prime is this. That is minus 2a1 sine 2x plus 2a2 cos 2x plus, we have this is a3x plus a4, exponential x plus a3 exponential x, right? So that is y prime. Now we'll start again for 8 plus 8, then we enter y. Y there is a1 cos 2x plus a2 sine 2x plus a3x plus a4 exponential x. Okay, this is equal 4 cos 2x, alright, plus 5x exponential x. Okay, so we now see that by opening these brackets, we will have minus 4a1 cos 2x minus 4a2 sine 2x. Then here we have plus a3x plus a4 exponential x plus 2a3 exponential x minus, this is now, with times here we have minus 12a1 sine 2x. Then for this we have plus 12a2 cos 2x. Then this times this will give us plus 6. Then we have a3x plus a4 exponential x. Then we will also times this plus 6a3 exponential x. Now, plus we use this to times also 8a1 cos 2x plus 8a2 sine 2x plus 8a3x plus a4 exponential x. Okay, we have opened up this. So this is equal 4 cos 2x plus 5x exponential x. Alright, and we want to collect like terms. We have cos here, a1 cos 2x. We also have another one here, 8a1 cos 2x. So what we have here is this one and this one can go, and then we write that this is equal 4a1 cos 2x. So we have been able to deal with this one. And so we also have 12a2 cos 2x. So that is the cos that we have. Now we can also write it in this way. See, we can also write it in this way. 4a1 plus 12a2. Can write it like this, cos 2x. It means the same. You are times this with this will be the same. Okay. Now we also look for sine. We have minus 4a2 sine 2x. Now we have minus 12a1 sine 2x. We are finished with cos. So this one is not there again. This one is not there. This one is not there. So what remains now is sine here, another sine here, and we have another sine here. But we see that this one, this is sine 2 minus 4a2 sine 2x, and this one is 8a2 sine 2x. So we can write like this: 4a2, that is this one and this one, 8a2 minus 4a2 will give you 4a2 minus 12a1, yes, then we have what? Sine 2x. So we have finished everything about sine now. This one. Then which one again? We have here 6a3x plus 4a. That is 6. We have one here, which is 7. Now we have another one here. This is 8. So if you add here, we have 15. And this is 8 plus this 14 plus this, we have 15. So we can write plus 15 a3x plus a4 exponential x. Now which other one do we have? This. We have one here. We also have 2 a3 exponential x. We have here 6a3 exponential x. So that is 8. So we can write plus 8a3 exponential x will be equal to 4 cos 2x plus 5x exponential x. Alright, so now, before we compare coefficients, we will now look at the arrangement. Okay, let's compare coefficients. Comparing coefficients. We now see that 4a1 plus 12a2 is equal 4. You know how? Call that equation 1. This is the coefficient of cos 2x, and this is the coefficient of cos 2x for this side. So it is 4 that is there. Alright. Now, we will also have that if we compare another coefficient, that is this. Yes. No, let's compare this first. 4a2, no, let me write it like this, minus, let me start with a1. minus 12a1 plus 4a2 is equal to 0. That is equation 2. Why is it equal to 0? Because there is no sign this side. So we have sign there, so it's equal to 0. Now, let's compare this. If we compare this, we have that we have, now see, this one, this particular place, we want to times it. Let's open here so that we can really get the coefficient of x. From here, we can say 15a exponential s plus 15a3x exponential x plus, to go this way, you have 15a4 exponential x, yes, plus 8a3 exponential x. Okay. Now, if we compare this please, comparing that please, we see that for x exponential x, this is the only thing that we have for x exponential x. So, can now see that 15a3 is equal 5, or this one is equal 5. That is because the coefficient of x exponential x is 5 for the right hand side. Another one, you can look at this, that 15a4, or let's start with a3, that 8a3 plus 15a4 is equal 0. 4 equations. Because we don't have exponential that is standing alone. So that's why we equate this for 0. Now let's start. From 3, that is here, you can find it easily that a3 is equal 5 over 15, which is 1 over 3. Now, if we put in 4, let's put it in equation 4, we'll have that a3, and so a3 is this, plus 15a4 is equal 0, which means that 15a4 will be equal minus 8 over 3, and then a4 alone will be minus 8 divided by 15, then times 3 will be minus 8 all over 45. You know, when you divide this, you can times it with this 3. So we have a3 and a4. We still need a1 and a2, but equation 1 and 2, there's nothing we can substitute from here. So what we'll do is to solve it simultaneously. Solve equation 1. Look at equation 1. 4a1 plus 12a2 is equal 4. Minus 12a1 plus 4a2 is equal 0. So then we can multiply 1 by 3 and 3 by 1. So if we multiply this by 3, we will have 12a1 plus 36a2 equal 12. Then this side becomes minus 12a1 plus 4a2 equal 0. Now, in that way, if we add these two, we know that this will go. So we have 40a2 is equal to 12, which implies that a2 will be 12 all over 40. Of course, 4 can go here 3 times. 4 can also go here 10 times. So we have 3 over 10. Alright. We can now seek for a1 by putting 3 over 10 in equation 2. So we have minus 12a1 plus 4a2, and a2 is 3 over 10, will be equal 0, which means minus 12a1 plus 12 all over 10 is 0. If we transfer this to the other side, we have minus 12a1 plus, minus 12a1 will be equal minus 12 over 10. Minus 12 over 10. That means a1 will be equal minus 12 over 10 divided by minus 12, which is equal minus 12 over minus 120. Now 12 times this will be 120. Okay, that means a1 is 12 cancel itself, 1. 12 cancel this, 10, because this minus and minus will go. This is equality sign. So minus and minus will go. So a1 is this. Then we can now substitute these values to yp. Yp was a1 cos 2x plus a2 sine 2x plus, let's go back to yp again. Yes, sine 2x plus a3 x plus a4 exponential x. So putting these values, we have that yp will be a1, and a1 is 1 all over 10 cos 2x plus a2 is 3 over 10. 3 over 10 sine 2x plus a3 is 1 over 3 plus 1 over 3x plus a4 is minus 8 all over 45 minus 8 all over 45 exponential x. So that is yp. And so the general solution will now be y is equal yc plus yp. yc is the first one. yc is the first one. What do we have? We have yc to be this. yc is c1 exponential minus 2x plus c2 exponential minus 4x. Okay, so we can then come to write it that y will be equal c1 exponential minus 2x plus c2 exponential minus 4x plus the yc, which is 1 all over 10 by light, because you see I can time this with this, so I'll write cos 2x plus 3 sine x, 3 sine x, yes, because I'm factoring out this term, okay, plus, that is the other one, which is 1 over 3 x minus 8 all over 45 exponential x. So that becomes the solution to the equation. It's very simple. It's very simple to follow. Just the left hand side is our usual homogeneous equation. We use that pattern. That is finding the auxiliary equation, and then you solve for the complementary function. Then the right hand side is making necessary assumption that will give you the right solution. Another method we are going to look at is method of variation of parameters. Now, given the non-homogeneous differential equation, y prime prime plus 2y prime plus y is equal to 3 exponential minus x, we are going to find a particular solution. Now, in this method, we are going to follow the same pattern, but in the complementary function. In the complementary function, we are going to substitute a function in the place of y1 and y2, so that we now use another approach to get a particular integral. This example will show. Okay, So we have y prime prime plus 2y prime plus y is equal to 3 exponential minus x. Now we know that this side, if equated to 0, will give us homogeneous equation. That is y prime prime plus 2y prime plus y is equal to 0. Why we keep this side first? So that we can find this complementary function. We can find the complementary function. Okay, we know that this will give us m2 plus 2m plus 1. Yes, of course, plus 1 will be equal to 0. And then we know that two numbers that we can add together is 1 and 1. And then 2 times 1 will be this. Meaning that m1 will be equal minus 1. m2 will be equal minus 1. This is coincident rules. We have the same thing. And then we see that the complementary function y will be c1 exponential minus x plus c2 x exponential minus x. That will be the complementary function. Alright. So, for the particular integral, what we'll do is, we come to this 1. When we come to this, we write that, let's use phi 1 exponential minus x plus phi 2 exponential minus x. That is what I am writing here. Is a kind of writing it in this form. Look at y1 phi 1 y1 plus phi 2 y2, and then I will equate this to 0. Also write phi 1 prime y1 plus phi 2 prime y2. I will now equate it to 3 exponential minus x. That is what I will do. You see, the first one, I'm representing phi 1 as a function in place of c1, and then c2 also replace phi 2 in this place. So if I do that, then I will have the function of the form. I equate the first one to 0, while the second one is equated to this particular function at the right hand side. So that is how we take the pattern. Then we can now proceed to the solving. Okay, so we have phi 1 y1 here is giving us exponential minus x plus phi 2 x exponential minus x is equal to 0. Then this one is the differentiation of this particular function, and if we differentiate here, we see we have minus phi 1 exponential minus x. Then this place is products. We have in product form. So, and that will give us phi 2x. To differentiate here, we have minus exponential minus x plus exponential minus x. Then we differentiate this, we have phi 2, which is equal 3 exponential minus x. And what happens is, here we can write it as phi 1 exponential minus x, and then here will be, see, here, when you times it here, we have minus phi 2x exponential minus x plus phi 2 exponential minus x is equal to 3 exponential minus x. But this place, we can factor out something here to write this particular equation. We can write it as minus phi 1 exponential minus x plus phi 2, then we have exponential minus x exponential minus x is equal to 3 exponential minus x. So these two equations now, this one and this one, this one Yeah, this one is the one we differentiate to have this, but this is the rearrangement of it. So we have this and this now. This particular one and this one is what we're dealing with. So what we'll do now is to take the determinants of this. Look at how we are going to determine phi 1. Phi 1 will be equal to the determinant of, you see, they will detach the coefficients. This one and this one. So we'll have exponential minus x minus exponential minus x. X is two coefficients. And then if we come here, we will have x exponential minus x. And this place will give us exponential minus x minus x exponential minus x. Alright. So this is the determinants first. So we will leave phi 1. This is the determinants. We want to take this determinant first by detaching the coefficient. See, the coefficient of this. Then this one is minus exponential minus x. Then you go for this, you have x exponential minus x. Then this one is here. So let's take this determinants first. Now determinants, we know that this times this will give us exponential minus x times exponential minus x minus x exponential minus x. We are times it like this. Minus, look at, minus exponential minus x, because this is times in this. So we have x minus x exponential minus x times minus x. This is what we are timesing, these two. And that will give us, this time this will give us exponential minus 2x. This time this will give us minus x exponential minus 2x. Then this will give us plus x exponential minus 2x. Yes, we have x exponential minus 2x plus, minus x exponential minus 2x plus x exponential minus 2x. So this one and this one will go. What we have here is exponential minus 2x. That is the determinant, exponential minus 2x. Now, to get phi 1, we will now take the determinant using Cramer's rule. Using Cramer's rule this time. So we want phi 1. What we'll do is to remove this 1 and fix the constants. If you are familiar with Cramer's rule, I believe you are familiar with it. So we put 0, which is this 0. And then we put 3 exponential minus 3x. Then we go to this side and put x exponential minus x. Then we have exponential minus x minus x exponential minus x. All over the determinant, which is exponential minus 2x. Now, taking this time this will give us 0 minus this. So we have minus 3x exponential. Okay, this one was, this is minus x. This is 3 minus x. Okay, so this time this is 0. Going this way, we have minus 3x exponential minus 2x all over exponential minus 2x. So this will give us, you see this, if we take this up, of course it will be plus. So we have minus 3x exponential minus 2x times exponential 2x. So everything here gives us minus 3x. Now, after getting minus 3x, we have to integrate. So phi 1 will be equal integral minus 3x dx, which is what? which is minus 3, yes, x squared all over 2. That is phi 1. Then we'll also look for phi 2. So y2, phi 2 will be in phi 2, we are going to remove this side and also put the constants. So we have exponential minus x, we have minus exponential minus x, then we have 0, then we have 3 exponential minus x, divided by exponential minus 2x. Now, this times this will give us 3 exponential minus 2x all over exponential minus 2x. And this will give us, if we carry this one up, we have plus. So everything becomes 3. Then, phi 2 will be integral of 3 dx, which is 3x. Okay, so now we see that y only will be yc plus yp, but only yp will be equal phi 1. You know that we said phi 1 y1 plus phi 2 y2, which means that phi 1, we have phi 1 to be minus 3 all over 2x squared. Then y1 was exponential minus x plus phi 2. Phi 2 is 3x. Then y2, for y2 we have x exponential minus x. That is from the function here, c2x before exponential minus x. Now, we see that we have minus 3 over 2 x squared exponential minus x plus, this time this will give us 3x squared exponential minus x. So, taking the LCM, this and this, we see that we'll have 2 times this. Of course, if we take the LCM is 2. So this cancels this, we have minus 3x squared exponential minus x. And then this is what? 6x squared exponential minus x, which is the same as dividing it by 2. So the whole thing will have become minus, now look at this. This minus this will give us 3x squared exponential minus x here divided by 2. So that is yp. That is yp. See what we have for yp. So meaning that the general solution will be, yc plus this will now be that y will be equal c1 plus c2x, then we have plus 3 all over 2 x squared, yes, then we have exponential minus x. You see, we are factoring out exponential minus x. So that is what we'll have at the end of it. And we want to look at another method of solving non-homogeneous differential equation with constant coefficients, known as operator D method. The symbol D is equal d dx. So this symbol, we introduce the symbol D, which is d dx. And if we have dy, it will be equal dy all over the x. Now, the symbol D does not have a value of its own. It is only a differential. So if I write maybe D cos x, D cos x means the differential. So the symbol D stands for the differential of a function. And you know that if I differentiate this, I'll have minus sine x. So if I have D squared cos x, it means I will differentiate cos x 2 times. So that would be the same as D minus sine x. You see, I've differentiated the first one. Which is minus sine x. Then I will differentiate again, which is equal what? Minus cos x. So that is the symbol. And we'll be using this symbol for some examples. Let's look at how we can evaluate some functions with operator D method, so that we can now see the application to non-homogeneous differential equation with constant coefficients. Let's pick some examples. So, examples, we are to evaluate D cos x, D cube x cube, D square exponential to x, D square x cube minus 6x plus 4. So we take the solution. For I, D cos x, we know is minus sine x. Now we have another one, D cube x cube. Now this will be equal to D square 3x square. I've differentiated the first time. Can also be equal to D. Then I have 6x. Then which is equal 6. I've differentiated it about 3 times. So D cube is telling me to differentiate it about 3 times. Now I have another one. This is the second one. This was the first one. So we have the third one, which is D square exponential to x. It will give me D2 exponential to x. That is, I'm differentiating the first one to have this. I have to differentiate again, which will give me 4 exponential to x. Okay, I will. D square x cubed minus 6x plus 4 will be equal to D 3x squared minus 6, which is equal to 6x. If I differentiate here, I will have 6x. So that is how the operator works. Now let's look at properties of operator D. Properties of operator D. If I have D of U plus V, it will be equal to du plus dv, where u and v are functions of x. That is one property. Another property is that if I have gn times gn of u as a function, it will be equal to gm plus n and then u. That is another property. Property number 2. Is property number 3. If I have dku to be equal to k du, that means the operator D is a linear operator. And don't forget that the D does not have a value of its own. So it's merely an operator. Alright. So we'll pick some example and see how we can also apply this so that we'll use it for solutions to differential equation. Now, using the properties of the operator D, evaluate the following. 1. D cubed plus 2D squared minus 3 times sine x. And then 2 is D squared minus 3D minus 2 times 2x squared. Then we also have D minus 4 squared sine x. 1, we have D cubed plus 2D squared minus 3 sine x. Now, since we know that operator D is a linear operator, we can times this to have D cubed sine x plus 2D squared sine x minus 3 sine x. Now here, we will now have D squared cos x. That is, if we differentiate this, we have, and then we have 2. Okay, this will be, yes, this will be 2D cos x, meaning we have differentiated here, minus 3 sine x. You know, this doesn't have D, so we can't differentiate that. Now here, we can have like this, D minus sine x plus 2 plus 2. And then we have minus 2 sine x. You know, we have differentiated this. So we have minus 2 sine x minus 3 sine x. Then we'll go with this again. If we differentiate this, we'll have minus cos x minus 2 sine x minus 3 sine x. So everything here becomes minus cos x minus 5 sine x. That is the solution to this one. And we can see that by property of operator D, we are able to differentiate this, knowing that we can multiply it with this. So that is how it works. Now, I'd like you to use that pattern and also do 2 and 3. Remember, here in 2 you have to expand it. This is like binomial expansion, so you expand it to have D cubed minus AD plus 16. Then before you start the multiplication. The next one we are taking now is the inverse operator T. Okay, recall that the operator D indicates the process of differentiation Therefore, 1 over D, that is the inverse of D, indicates the process of integration. Indicate the process of integration. So, if I have 1 all over D squared, this 1 all over D squared indicates double integration. That means I have to integrate it 2 times. So So that is how it works. If I have 1 over d cube, then I have to integrate it up to 3 times. So let's look at example how we can also integrate using operator D. Example, we have evaluate 1 over d sine x, 1 over d cube, x squared plus 2x minus 3. The solution is 1 over d sine x. You see, that means integration of sine x, and that will give you minus cos x. Of course, if we integrate sine x, you have minus cos x. Now, for I, we have 1 over d cube x squared plus 2x minus 3. We will have 1 over d squared. Then we have x cubed all over 3 plus x squared minus 3x. So I have integrated the first time. Of course, if you integrate this, you have this. So that will be the same as 1 over d. If I integrate this again, I'll have x raised to the power 4 all over 12 plus x cubed all over 3 minus 3x squared all over 2. Now, integrating this again will give me x raised to the power 5 all over 60, that is 12 times 5, plus x raised to the power 4 all over 12 minus 3x raised to the power 3 all over 6, which is the same as x raised to the power 5 all over 60 plus x raised to the power 4 all over 12 minus x cubed all over 2. So that is how we can integrate. It's very simple. It's very simple to integrate using operator D. Alright. We want to take a theorem that will help us use it to evaluate some functions. Theorem. LD exponential kx will be equal LK exponential kx. Now, let's prove. We know that d exponential kx will be equal k exponential kx. Okay, let's call this 1. We also know that d squared exponential kx will be equal d k exponential kx, which is equal k squared exponential kx. You know, from here, we differentiate one time, we reach here. Differentiate it again, we reach here. So we have this as equation 2. Now, 1 plus 2 will give us, or even you say 2 plus 1, still the same. D squared plus d for this side, which is equal k squared exponential kx plus k exponential kx. Of course, we can write this as k squared plus k exponential kx, which is the same as lk exponential kx. Now, if LD denotes d squared plus d, then we can say that LD will be equal lk exponential kx, where lk is k squared plus k. Alright, now let's see how this theorem will help us to evaluate some functions. Alright, so example, evaluate the following: 2d squared minus 4d plus 5 times exponential 2x. That is number 1. Now, remember that from the theorem, LD exponential kx will be equal LK exponential kx. That's what we prove from here. So we'll use it. So that in this one that we have 2d squared minus 4d plus 5 exponential 2x, then we will be the same as 2k, you see, LD become LK. So what is k in this context? 2. Kx, 2x. So that means here we will have 2, then we put square. Alright? Then we also have minus 4 times 2 plus 5 exponential 2x, which is the same as, you see, this is 4 times it. We have 8 minus 8 plus 5 exponential 2x. Of course, everything here becomes 5 exponential 2x. So that's the usefulness of the theorem. Now, I'd like you to try this. It's very simple. This is k is still here. Just fix it. We want to pick another theorem that will help us to understand operator D in using it to solve differential equation. Now we have that LD exponential kx of u will be equal exponential kx L d plus k u. Now what I mean is, if I have a function and I have exponential kx, I have u is also a function, it will be equal to exponential kx, bringing this exponential function out, then I have L d plus k times u, which is the function, another function also. So in this, I would like us to pick an example that will help us, because this is where we want to apply operator D in solving differential equation. Let's pick an example. Now, example, we evaluate d minus 4 exponential 3s s cubed. Another one, number 2, is 2d squared minus d plus 3 exponential minus 2s s squared. Now let me pick solution of 1. Using this theorem, we see that d minus 4 exponential 3x s cubed will be equal to exponential 3x. You see, I'm bringing exponential 3x. Then I have L d plus k, and k in this context is 3 minus 4. Then I have u, which is in this case exponential cube. That is how we evaluate it, so that this will become exponential 3x d minus 1, got that, d minus 1 s cubed. So, and that will give us exponential 3x. Now this time this will give us d s cubed minus s cubed. That means what we have is differentiation of this. We differentiate it one time. If you do that, we'll have 3s squared minus s cubed. Minus x cubed. So now this becomes the solution, because this time this and this time this is the same thing as factoring it out. So you can see how we do. And so this one will be the same. In this case, you take the exponential back. Now k in this context is minus 2. So what you have here is d plus minus 2, that is d minus 2 square, minus d minus 2. Then we now use this particular function s squared to multiply it, and then you differentiate where necessary. So I'd like you to also pick this on your own and try using this pattern. It's very simple. 2g plus k, and k in this context is minus 2. Then you square minus d minus 2 plus 3. Then you use this function and multiply it. So anywhere you see this square is differentiation, differentiating it 2 times. Alright, so let's see application. So we look at application of operator D in solution to non-homogeneous differential equation. Now we know that non-homogeneous differential equation with constant coefficients is of this form: a sub 2 d square y all over the x squared plus a sub 1 dy dx plus ao y is equal f of x. So if we can write this in terms of d, then we see that we will have it in this form: a2 d square plus, or let's put here d square y, so plus a1 dy plus y. Let's put this y is equal f of x. Now if I factor out y, I will have like this: a2 d square plus a1 d plus ao y is equal f of x. Now making y subject of the formula, I will have that y is equal f of x all over a2 d square plus a1 d plus ao, which I can also write as 1 all over L of d. Then I have f of x, still the same. So L of d is this one. Now with this we can solve non-homogeneous equation. Remember, the left hand side is solved in the usual pattern of homogeneous equation. Now let's take an example and see how we can apply operator D to solve non-homogeneous linear equation. So let's look at this example, how we can apply operator D to solve the differential equation. Now solve the equation d square y dx squared minus 4 dy dx plus 3y is equal exponential 2x using operator D method. Solution: we have d square y all over the x squared minus 4 dy dx plus 3y is equal exponential 2x. Now the first thing we'll do, we'll consider the left hand side as usual by equating it to 0, so that we solve the homogeneous part first. Then we'll have d square y the x squared minus 4 dy dx plus 3y is equal 0. Now let y is equal exponential mx, so that y prime, that is the y dx, will be m exponential mx. So y prime prime, which is d square y all over the x squared, will be m squared exponential mx. Alright, so if we put that in this, we then have that m squared minus 4m m squared exponential mx, yes, minus 4 minus 4m exponential mx, then we have plus 3, and y is exponential mx is equal 0. So we have that m squared minus 4m plus 3 exponential mx is equal 0. Now, m squared minus 4m plus 3 is equal 0. Exponential mx is not equal 0. So, we'll solve this. And this we know by quadratic equation that this one can give us m minus 1 and m minus 3 is equal 0. So that m is equal 1 or m is equal 3. So, we have that. Then, we now see that the solution, the two linearly independent solution will be exponential x and exponential 3x. So that is what we have. So that the complementary, the YC part will be C1 exponential x plus C2 exponential 3x. Now, we want to solve this part. Now. And to solve this part, let's write this in terms of D. We are finished with the other part. So we can write it in terms of D to enable us to solve this with operator D. So we now say that this square y, look at this, we know that we can write this second order differential as this. Minus 4 dy plus 3y is equal exponential 2x. So that I can write this as d square minus 4d plus 3. Then y is equal exponential 2x. So that y will be equal 1 all over d square minus 4d plus 3 exponential 2x. And we recall, we just finished a theorem. Recall that LD of exponential kx will be equal LK exponential kx. So we just finished. Look at the first theorem that we proved. So that what this means is that we can write this as y is equal 1 all over, of course we put k. For our k here, see our k, this is 2. So we have 2 squared minus 4, and we have 2 plus 3. And this is exponential 2x. So that will give us 1 all over 4 minus 8 plus 3 exponential 2x. Now 4 minus 8, look at that. This plus this 7. So we have minus 1. So that will give us minus exponential 2x. This is minus 1, which is 1 divided by minus 1 is minus 1 times this, you have this. So that is yp. This y is yp. Therefore, the general solution will now be the general solution y. It is equal to yc plus yp. So the general solution will become, we go back to here where we have c1 exponential x plus c2 exponential 3x. Then we have the yp side, which is minus exponential 2x. So in fact, you can use it to solve plenty differential equation, but we don't have much time for now, so you apply it using different theorems that we have done so that you can solve other ones. Okay.